Cool. Okay, so with the transformer, you have to understand three things, right? So we know from before in a transformer circuits, if this is your input power, oh, I hate this pen. Yeah, sorry. Yeah, so if this is your input power here, I'll use the documents. I do not like this pen. I forgot that. Alright, so right up to here, you just break it apart piece by piece. So you have your inputs here, right? So there's our input voltage and its phase voltage because it's a single phase transformer. So in the lab or in the exam or whatever the cases, you have two ways in which it could give you this. So you have to pay attention to this, right? The first way they could give it to you as in phasor form. So they will say V angle theta. So example, I might say 2 angle minus 2.3 degrees. So they will actually give you the voltage like this, or they will just give it to you like a flat value, right? Both of these, they mean the same thing, so don't get thrown off center if it gives you the voltage in phasor form. It's the same thing, remember, it's AC current or AC voltage you're dealing with. So if it get like this, just operate it like normal. It doesn't change anything. All the equations and stuff will be the same. You just have to put your calculator in complex mode. Assume everybody know how to do that by now, right? So that's work. Well, you should do the lab, so you should know how to do this already. So just know he could give you the voltage with an angle. Some people, or most people, are accustomed with the voltage being at an angle of 0, which means the voltage is at the reference. So you don't really have to care about the angle, but sometimes he could give you the angle of the voltage. So don't get thrown off center. So that's the first way they could give the voltage. They could give it to a V with a theta. The second way is just the magnitude. And have no third way. So that is with the voltage. The other thing which we get into with this circuit, right? So when you have your voltage being sent into the system itself, you have this current here, this first current here. This current is called IN, which is your input current, right? This is before any losses in the circuit or your no load losses, and by extension, the current actually going into the coil of the transformer itself, right? So this IN is before everything. Some people just mix these things up. So as it continues to flow into your input current at this junction, it splits into two directions. The first is called your no load losses, where your no load current, which is basically current when you have no load, which is your open circuit test. And then the other currents is the current that actually going in, it could say into your transformer, but this is already in the transformer. So you can kind of think of this purple current as the current that going into the actual coils, or the majority of current that going into the coils itself. So the labeling for this is I1, right? So you have to understand these labels, because in the exam they will tell you to calculate these things, so you have to know how they relate to each other, right? And in this circuit here, going into the no load part, it splits into two directions. So your first direction, you label it IW. So these are your heating losses, your I squared R losses. And this one here is IM, your magnetization losses. So magnetizing losses isn't dissipated in the circuit. You don't lose any reactive power. Like that doesn't exist. You don't lose reactive power. You only lose real power, which is power across a resistor. This is an inductor. So when you're doing your losses calculations, you do not include any inductor losses in your calculations, because this is losses due to energy put into generating the magnetic field. Like that is it. If you switch off the circuit, that magnetic field just go back. It will just shrink back down. So the energy isn't really lost It's just stored in a different form, which is the magnetic field, right? So just note that this arrow, heating losses, and you call this JXM. So there's your magnetizing losses. So just note you don't lose reactive power. Right? Reactive power just circulates in the circuit itself. It isn't lost. I squared R losses that I heat it. But if it hot, you lose the energy, right? Because it dissipated onto the circuit that never coming back ever. Okay? So your I no load, it splits into two. So you have your IW and you have your IM. So I think you all went through hysteresis losses and eddy current losses. So these two models those things. Your hysteresis or hysteresis, however you pronounce it, and your eddy current losses. So by now most people should know what those things are, but just read the notes, right? I wouldn't really use the session to go through those things. Okay, if that come in an exam, they're just asking to define what eddy currents and hysteresis losses are. That is all that going to come in the exam. It have no calculations for those questions. So go on, you're going to come for like 2, 3 marks anyway. Okay, so right, so we have input voltage creating an input current and then the input current splitting into a no load. So you can actually generate an equation for your no load current. So your no load current will basically be a IM plus G, well not IM, IW, because that's the real parts. It will be IW plus G IM. I think most books will have the J with a minus, so but it really doesn't matter too much. So this is your equation for your no load because that is the current that splits in these two directions here. And then from the circuit now, you're just going to continue. So when you're inside the transformer now, you have a different set of losses. So when you reach here now, you have another resistor and you have another inductor. And then you have your coil. And this coil goes back to here. So far in the circuit, we have this I1 current, which is basically your input current minus your no load little current here, because it's small. So this I1 is the current that flows through something called R1 and JX1. So these two are your losses in the circuit due to the core. Right? So this R1 and this X1 is for the coil itself. Right? This is actually what your impedance and stuff, your losses in the coil itself is. So the coil, the million and one turns in the coil, when you pass current through that, you have heating losses. And this JXM, so this X1 here, which is the JX1, what this comes from is because you have a coil, well actually two coils, and they have a magnetic field that is generated. And these magnetic field lines, some of them don't cut the other coil fully. And if it's not cutting it, not doing anything, so you're losing energy or potential energy due to those losses. So that is modeled by this X1. So this coil here going to generate a magnetic field, but all the flux lines that comes from this not going to cut the secondary, all of them not going to cut. Some of them just going to be passing through empty space. So you're going to have losses in the circuit. And this is just your core losses, which is just copper losses, I squared R losses, current through copper, heat losses. This one here is basically just the flux not cutting the coil of the other part. So if not cutting and not doing nothing, right? So that's what these two model and X and I1 passes through these. Okay, so follow me here. This I1, when it goes through the R1 and this JX1, you have this point here. This point here is very important. Why? Because this, whatever this voltage is after all these losses, is actually the voltage this coil will see to then use the turn ratio to get across to the other side. So you have to understand this point. So this point, in theory, they normally call it E1. So just be careful with the terminologies. If you use V1, you wouldn't really lose any marks. But just know this point here after all the losses is basically the voltage the coil sees, right? And then obviously we know the other side has another coil So now well, turns ratio. So I think most people know your turns ratio by now. So your turns ratio basically how gives you how the turns in the primary and secondary, the voltage in the primary and secondary, and the current in the primary and secondary, how they relate to each other. So the equation for it is N1 on N2 equal to V1 V2 E1 on E2. I'll explain what E1 and E2 is, which is equal to I2 on I1, and all this just equal to K, which is a constant. Okay, so you call this your turns ratio equation. Easy way to remember it, everything on top is 1 and 2 at the bottom except the current, they just swap. So V1 and V2, those values that you get in the question itself, these are your rated voltages.
Daniel, I have a question.
Yeah, sure. Yeah,
So IW is the same as IO because in the lab I was using IO.
yeah, that's correct.
And
Mm-hmm.
if they give you the angle for the
Mm.
voltage, right?
Right, right.
Where where we will use that.
Right, so the angle for a voltage just means that the reference for the voltage just at a different point. So that wouldn't change anything in the question at all. Wouldn't
Okay.
change anything at all. It'll just give people that to throw them off center because now they're trying to overthink everything. But don't let it throw
Okay.
you off center. We will get to it just now, but the only angle that you care about is the current angle because the current angle will basically give you something called a power factor. You all remember
Mm-hmm.
that?
Yeah.
So your current angle is where you care about because most of the time your voltage is at a reference. Let me just show you what I mean by that. So V is always at a reference, which is at 0 degrees, right? So I don't know if from your reading you heard something called lag and lead. So those two things kind of gives you the two possible ways the angle could be with a reference from the voltage. So it could be on top, which is a positive angle, which is leading, and it could be at the bottom, right? So this will be minus theta, and this will be positive theta. You will rarely ever find a positive angle for current. That's like real rare. Not even so rare, I don't even think that even possible to get a positive current. Because a positive current means that your current happening before your voltage. Like, I don't think that could happen. I think you need the voltage, but that's just too complicated. But most of the time you'll have a negative current, which means it's lagging. So, which makes sense. But that in mind. If they give you a new angle for the voltage, that's not going to change anything because if you put this at 2 degrees, the entire angle just going to shift to compensate for it. So it literally just going to shift around. But it's not going to change the price of cheese in the question. But we'll get to the power factor, but it's a good question, right? So I continue. So we had E1. So this E1 is very important. Most questions ask you to get it. So once you have E1, E1 is the induced or the voltage seen at the coil after all the losses in the circuit. Okay, remember you have a voltage, you have losses, and after these losses, you have the voltage that is left, and the voltage that is left will be the voltage the coil sees, and that voltage the coil sees is what they're going to use the turn ratio to get on this side. A lot of people has made a mistake. If the question say 220 volts rated at the input, they always think that it will be 220 volts at the coil, which is wrong because you have losses in the circuit. So you're not going to get that exact 220 at the coil to transfer it across to get the rated voltage on the other side. Okay, so just keep that in mind. Continue with the process. After you use your turn ratio, come across on this side. You have E2. Same process. You have R2 and JX2. And same thing on this side. The X represents the induced magnetic field on this side. Some of them not cutting the other coil, so you have losses. And R2 just I squared R losses. Current in a copper wire, heat losses. Okay. After those losses, you have this voltage here, which we call V2 and which we call V out, which you could also call the terminal voltage. I have like multiple ways that I say it, VT. Multiple ways, right? This voltage here is the voltage your load sees. So we'll put our load. So that is the voltage your load sees. Well, everything else from there is just calculations, right? So your load, which is what I'm coming to now, when they give me a load in the question, they have to give you two things. The first thing I have to give you is the power factor, and then from the power factor, it will either be a lag or a lead, which is just telling you the angle, and then on the load, they will also give you probably an amount or a magnitude, which you will see in the tutorial. How it does work is, and I'll just move real slow. For the load, the power factor is cos theta load. That is how we'll give you the power factor, right? That angle is basically the angle for the current. Well, this here, real important. Anytime they give you a power factor for the load, the angle for that is the angle for your current. Just keep that in mind. That's that they're going to basically boil on real questions if you're given a question like that. So your load always say 0.8 power factor lag or something like that. Convert that to angle. If you want to convert something to angle, cos inverse of the value, you get the angle, right? And then if they say lag is negative and will lead us positive. That's for the angle itself. Okay? Now, well, the magnitude is just complex form. So that is load. Anytime they give you the load power factor, don't get confused. Take the load power factor, convert it to angle. If it's lag, it will be negative of the angle. And then you need to calculate your current magnitude, which is an entire story by itself, right? But just know, if they give you the load, you could actually calculate what the power factor and the angle is, and you could go straight back to the beginning, right? So let's just start over, do it one more time and jump straight into the tutorial. So now would be the best time to ask any questions. You all can stop me, eh? Don't let me just talk, you all can just stop. Because here, as you all are careful. So the VN will basically just phase voltage. So you have your neutral and your line, which you all know already. Um, I don't know if you all, I don't think you all need to know that. How to go from a line to a phase. But just to write it down, V line or V phase is root 3, well, V line and root 3. There's just a little extra equation. I don't know if you could bring a question where he gave you a line voltage and you had to go to your phase voltage. But just know a single phase transformer needs phase voltage. So if they give you a line voltage, you just divide it by root 3 and you get a phase voltage, okay? So they get a phase voltage. 1.
So
2.
question. So
Yes, go
how
ahead.
does know like which is always use phase voltage?
Right. Can you repeat the question? How, what?
Like for these type of question, right? We
Right.
always use phase voltage because I
Yes.
was kind of confused at when we would use this conversion.
Yes.
So
So,
say like
go
if
ahead.
he
Go
give
ahead.
us a question,
Right.
if he give us a question and he have line voltage, we
Mm-hmm.
just had to convert it to phase voltage
Correct.
and then proceed with the
Correct.
calculations.
Correct. Because it's a
Okay.
single phase transformer. So I don't know
Oh,
if you all remember from the lab when you all did induction, you all of us saw the three stack variac, the variac with just three stacks in it for induction. Each phase need a transformer. So if you have a three-phase transformer, it's basically just three similar single-phase transformers. So a three-phase transformer doesn't exist. A three-phase transformer is just three single-phase transformers in any combination. Okay? But yes, if it's a single-phase transformer, that means you need a line and a neutral. Okay? If you put a line to line, I don't think it will work. That'll be pressure. Because a line to line basically means that you don't supply a higher voltage. But I mean that is core electronics and electrical. Don't think you'll go in that end up. But yes, if they give you a line, you have to convert it to the phase and continue everything after that. So let's not stray too much. Yeah. So after you
Answer.
get, go ahead. Any more?
Nah, just say thanks.
All right, no problem. So I'll ask all the questions. Ask it doesn't matter. Cool. So this is phase voltage here. Go and give your input current. And you know the first place that the current gonna go is your no load. So basically think of this as you're trying to cook and you had to like go in the grocery and get all the supplies before you start to cook. That is your no load current. So it's kind of like setting up your magnetic field and stuff for you. And once your magnetic field is set up and you have your losses, you always have losses because once you pass current through a wire, you'll get heated. Okay? And just remember, reactive power isn't dissipated in the circuit, it just circulates back and forth. Okay? So the only losses are real losses. So after you know which is small, the rest of current is your I1. So technically, I1 is basically just your input current minus your no load current. That's something you could remember. Once I give you input current, do not, I repeat, do not use that as your I1 because it's not the same thing. Because you have to subtract the losses for your I no load. Yeah, just remember that. A lot of people have made that mistake. It's not the same thing. Okay. Alright, so after you get your I1, that I1 is going to flow through R1 and X1. You can't get a loss. And the voltage that is left is E1. Use your turns ratio. They will most of the time give you V1 and V2 in the question, right? They will rarely give you N1 and N2. That's this one array. This one you will most of the time have E1 and E2 just your induced voltages on each side. So you have E1 here and E2. That is the voltage the coil seeing. The coil not seeing this input voltage. The coil seeing the voltage left after your losses. Right, so you transfer turn ratio. You have a induced and this going to go through these losses and you're going to end up with a V2 on the other side. And that is the voltage the load going to see. And the load, when the question, they'll always give you power factor of the load, or they can give you the magnitude of the load. Either way, your power factor of the load can give you cos theta of the load, and then you just convert that to the angle, and that is the angle for your current. That is how it does walk through the entire circuit, back and forth. It really matters which way you go. Okay, so let me just go through one more thing. So any question, sometimes they will say you have to refer the impedances on one side or refer it back to the other side or some matter like that. So you have two ways in which that could happen. So I'll leave it with the losses for now. Just know it's still there, just to keep the calculation simple. Well, not the calculation, the drawing, because I hate drawing. Okay, so you have this is your primary and this is your secondary. So in this, I'm just zoom out. So what we did here, these impedances here, the R2 and the JX2, we referred it to the primary side. We just carry it across to get an equivalent impedance on one side. So you don't have to account for the impedances twice. You just account for the ones, you lump all together, and you account for the ones, and you're happy with life. So how to do that now? It's really simple. So the trick is you have something called your turn ratio factor. So if you're going from the secondary to the primary, so the ratio is n1 on n2 squared. So that is when you're going from secondary to the primary. And then if you're going from the primary to the secondary, it'll be n2 on n1 squared. And you best just multiplying it by whatever factor you need. So this is primary to secondary. The trick I just use this numerator here. The square and all is still the same, but the numerator always telling you the side I go in 2. So if I go in 2, the primary side will be n1 on top, and the n2 at the bottom, and it will square the whole thing. And if I go into the secondary side, the n2 will be on top. That's literally all you have to worry about. The whole equation itself is kind of the same. So if I wanted to, let's run through to the corner. So if I go in from the secondary to the primary, I'll just do 1, right? Because you can understand the concept. So if I go in from the secondary to the primary, you'll have r2 prime, because it's not r2 anymore, it'll be prime. And it'll be r2, and you multiply on that. So you go into the primary side, it'll be n1 on top, and you square the whole thing. Same thing for x1, x2 prime, because it's not x2 anymore. It will be the x2, and you go into the primary side, so it'll be n1 and n2 squared. And that's basically what it is. Just note it's prime because on the side it's not supposed to be on. You multiply them by its current value and the turns ratio factor. The other way is if you're going from the primary to the secondary, so you'll have r1 prime, because not r1 anymore. It will be r1. You go into the secondary, so it'll be n2 on top. And well, same thing for the x1 prime. x1. You go into the secondary, so the n2 will be on top, and the n1 will be at the bottom. Yeah, and that's basically how you refill stuff back and forth over and over, right? So that's really all you have to know. And just once you refill it, you're basically gonna get a lump. So you end up with Req, which is the equivalent, and JXeq, which is the equivalent impedance. Because when you refill stuff on either side, you basically have the sum of the R's on either side. So if you go from the secondary to the primary, you will have ZEQ. So you're going from the secondary to the primary. So the primary have the R1 and you have your R2 prime. So that will give you your R plus. So you have your JX1, got that there already, plus your JX2 prime. And basically that's going to give you your JXeq. So on the out, you're just going to end up with a R equivalent plus a JX equivalent because they're just summing. And it really matter what side they're going on to. Once you refill it properly, just add it up. And you just end up with one resistance and one inductance, which is the equivalent impedance on whatever side it is. Okay, so hope that was helpful. So what you need to know from this is how the voltages and currents can work. When any primary side is the easiest one, right? Because once you have a Vn, once you calculate your I1, not In, I1, whatever voltage here, once you use the turns ratio on it, you notice you have no impedances here. So if you generate or use your turns ratio and you get 223 volts here, that will be the voltage at the output because it have no more losses, like it have none, because I already account for it on the side, which is the beautiful part of it. So this is easier one because once you use your turns ratio, once you get this E1 here, you kind of set, because once you use your turns ratio on it, you already getting your output voltage because it have no impedance. And the secondary, because you refer it to the primary, which means you account for it already, so you don't have to worry about it too much. Okay, same way if they had referred to the secondary side, which is referring the primary to the secondary side, that also makes the calculations a bit easier just on the primary side. Okay, so if you have your Vn here, we have a voltage here. If this is 200, you have no losses here. So this literally is going to be a E1. Okay, and then once you use your turns ratio, you get E2. But now, because you have these losses, you have to account for all the losses in the circuit on this side. So this is I2 now, so Just keep that in mind. Once you have your I2, the losses across here will give you your V out. So this way makes it easier for the input because you have no losses. And this one on top here makes it easier for the output. So any question, most of the time they will tell you what side it already referred to. So you don't have to worry about it, you just have to know it lumps everything together. So you don't need to account for it twice. Okay? So that is transferring impedances. Alright, any questions on that? Alright, cool.
So you mind just running it back over one more time?
Yeah,
Kinda,
yeah, so
yeah.
sure.
Thanks.
So in the circuit itself, I'm gonna ask you some questions, right? So if I wanted to calculate or transfer R2 onto the primary side, let's have a factor is N1 and N2 all squared, right? That is a factor. If I go into the primary side, it will be N1 and N2 squared multiplied by R2 because I go into this side. So if I go in from this R2 here onto this side, it will be R2 prime because when I reach on this side, it will be the prime R2 because it's not R2 anymore. And it's R2, but I need to multiply by a factor because it's not going to be the same on both sides. So the factor is basically just your turns ratio squared in the correct formation. So the trick is if you're going towards the primary side, which is the N1 side, the N1 will be on top, and well, the N2 will be at the bottom, and it's squared. So basically just going to give you the secondary impedance or the secondary real part on the primary side. The voltage will or the value itself will change because of the turns ratio part. Okay? And then same thing if you as the same equation, if you wanted to find the x2 prime, it would just be x2 here, and the turns ratio part will be the same. And then for the primary, if you're going from this side onto this side, since you're going to the secondary side, it will be n2 and n1. So the entire equation here, you're just using it for r1 and x1. So it'll be x1, r1 here, but this part here will just be n2 and n1 instead of n1 and n2 because we're going to the secondary side, which is n2. So the numerator will just have the side that you're going towards, and the denominator just have the side that you're coming from. Okay? That's kind of how I just think about it. Okay, once you have
Also,
that, yeah, go ahead.
so basically, the turns ratio that will just flip depends on what side you're going from or
Mm-hmm.
to.
Yeah,
Oh,
so
and
yeah,
that's really it.
correct. So and that will
Okay.
give you the equivalent impedance seen on the other side. Because it wouldn't be the same. Just note, to keep it simple, this is what you have, right? You just need to know what this factor is. And the easiest way to think about it is the top kind of telling you where you're going to, or the side you're going to, and the bottom telling you where you're coming from. Once you remember that, don't forget to square it, right? Once you remember that, you'll be okay. Alright, any more
Right.
questions?
Thanks. I also saw another thing. You're recording this?
Yeah.
Or
Yeah.
okay, cool.
Mm-hmm.
Thanks.
No problem. Yeah, but so far, just take away the is an equation, but it's easy to remember. Just know most of the time they already give it, you refer to one side. So you don't really have to worry about the equivalent part. You just have to know how to refer it. Okay? Alright. So the last thing or the last equation they have to know is something called a um, apparent power equation. So this is the end all be all of most equations, right? So S is the apparent power is equal to VI. The brackets and stuff, that means the magnitude of it, right? S is equal to VI. This comes in handy when you're operating at full load. When you're operating at full load, everything is at rated. Rated voltage, rated current, rated output, load, everything literally at rated, right? But this is a good equation to know because most of the time you could get your magnitude of your current, and the only thing that will give you the angle for your current is your load or the input current or voltage, whatever they give you in the question. Okay, so from that you only two equations you had to know from. This is your voltage regulation equation, which is your V no load, which is rated. They will always give you this minus your full load, which is basically the load that they operating it at, divided by your full load voltage. And yeah, the second one is your efficiency equation, right? And well, efficiency by definition is your P out divided by Pn. If you ever forget which one going on top or the bottom, your input power will always be more than your output power because of losses. So, because you have losses in the circuit, you know for sure the numerator have to be the smaller value. Yeah, that's a easy way to think about it if you're kind of getting confused whether it's P out or PN or P out or whatever the case is, right? So this kind of splits into two equations. So the other one you have Pn minus your losses divided by Pn, which is basically the same thing because your input power minus your losses is your P out. Yeah? And then the other equation that you could use is your P out divided by your P out plus your losses, which is the same thing. If you add the losses, say output power, you're going to end up with your Pn. And what P out is P out. So these are the two ways in which you could use it. When will you know how to use it? You will use this one when you have more info for the primary side, which is the side the Pn coming from, right? And you will use this one when you have more info for the secondary. And that's all. That's literally how you will know which one to use. If you have I1, V1, you have your input power, which means you have your um, power factor. You just use the Pn form of it. And if you have V2, I2, your load, which you get a power factor from your load, you will just use that one, right? To matter which one. But just use the one that you have the most information for. Okay, and the last thing before we run through the tutorial questions is your power factor. So you have two ways in which you could get a power factor, right? The first is from the inputs. That's literally how most questions will be. And I'll show this already. So you have I angle minus theta. This here is your power factor. So cos theta is equal to your power factor. Theta is an even function, so the negative it doesn't really matter for cos. So it doesn't matter if it's positive or negative. The power factor will always be positive, right? So that is your inputs. You can get the power factor from the input current, which is just the angle for the current, and then the other way is you could get it from the load. And with the load, they will give you, they might say power factor, lag, or lead. And basically with that, remember, cos theta is the power factor. And this giving you the angle for your current on both sides, which AK is the current for your um, input. So everything gonna be at that angle. The angle is basically what the machine operating at. So it doesn't magically change any question, right? Okay, so we have knowledge. So we look to apply it. So that's no
So,
power. Yeah, go ahead. Question.
um,
Go ahead.
so for the power factor for the input side, right?
Mm-hmm.
When we calculate the current in complex form, right?
Mm-hmm.
That angle what we get, right? So we had to take to find the that angle That whole angle just represents the power factor.
Yeah, cos theta, which is the cos of the angle, is equal to your
Mm.
power factor. So cos inverse of your power factor will give you theta, which is the angle itself. Yeah.
So wait, wait.
So
Um, so
so
this
you
angle here, right? We had to take the cos of it
to get the power
or
factor.
to get the power factor.
Yeah, I will show you why, right? The reason why I need the power factor is because your efficiency equation, the equation for power is V I cos theta, right?
Right.
This cos theta is your power factor. The values for your power factor will be like zero point 0.8, zero point 0.9, zero point
Yeah.
0.7, and the stuff, right? That is actually power factor. That is cos theta, the entire thing, right?
Right.
If you wanted to know the angle for the current from this, so like say in a question, let's say the power factor is 0.8, I just need to do cos inverse of 0.8 and I'll get the angle. Also,
Right. Yeah.
follow me? So
Yeah.
if they give you the input, most of the time, if they give you the input, they will give you the angle for the input. They won't give you the power factor for the input. Because a power factor, by definition, deals with a load. Okay? But
Okay.
if a input, they will give you the angle. If they give you the angle, you could convert that angle into the cos theta to use in your power equation. Because you need that to calculate your efficiency. Follow me? So once
Okay.
they give you the input current, you could just use that and go straight through the circuit with it. But anytime we're
Oh.
talking about efficiency, if you're dealing with the V1, I1, you have to use this as the cos theta, the input, which you will know what it is, because it will give you the input current already. And then the other way is if they give you the power factor, the load. With the power factor, the load, they will give you two things. They will say 0.8 power factor lag or lead. From this, you can calculate the angle, which is cos inverse as 0.8, right? And then from that, you can calculate whether the angle will be negative or positive based on the lag or lead. Yeah. So if it's lag, it will be negative or whatever angle this is. And if it's lead, it will be positive or whatever angle this is. So anytime they give you any load, you have to go back to the angle. If they give you the input, you have to go back to the power factor. Because that's based on what the equation wants and where you had to use, right? These questions will be set up in a specific way. So I could tell you if they give you the load power factor, most of the time you have to use that to calculate the angle for the current to go backwards. If they give you the angle and stuff for the input, most of the time you have to convert that to the power factor, which is the cos theta, because they're going to ask you so many questions to calculate the efficiency. Okay? Okay, any
Okay.
more questions? Cool. Nice. So, okay, go through some questions. So, I did like all the questions already. So, I was going to skip the theory questions because I don't like theory. Like, and this degree, like, 3 years now. Theory, it could only give you like 10 marks in an exam. Know your theory, yeah? Don't get me wrong, but focus more on your questions because the majority of your marks will come from. If you're not strong in your questions, don't worry about theory because you're gonna be memorizing theory for no reason. Okay, so you all know how star and delta does work in terms of the operation of it. So I think most of you all probably know. We'll go through that another time. I'll take a look at the diagram. Alright, I'll give the drawing on the bottom here so you all can kind of look and see how I connected. If any of you are confused about the drawing what I put in, just message me. I'll go through it with you. I wouldn't spend time on that. You can look at the drawing and see how we connected. Each of the coils, you have three coils because it's a three-phase system. And if there was a star, you have to draw any commons together. And well, L1, L2, and L3 coming in. And then the delta is basically just everything in kind of like a loop. So once you start one through the loop, connect to the next one through the loop, connect to the next one through the loop, when you go straight back up to the top. It's like a circle by the delta. So you kind of look through the patterns and see. Alright, so I'll go through these questions. I want you all to stop me if you are confused. Just literally stop me, right? That's okay, because everybody will benefit. Some people may not have the courage to ask. So if you feel impressed to ask a question, ask the question, okay? Okay, so the question 5 is basically just talking about your no load calculations, your open circuits. and your short circuit test for your transformer itself, right? So any question if they give it to you, you need three things: power, and you have your current, and you have your voltage. Same thing from your lab when you did it. Like the three things you always measure. There's just one smaller than the other one. In an open circuit test, you'll have a higher voltage and a small current most of the time. And for a short circuit, to keep it safe, you'll have a relatively higher current but a very small voltage. Because as you all remember from your lab, for the short circuit, that's a small change in voltage. Will give you a mammoth change in current. The current you all measure is not himself what the actual current is. If we actually have a short circuit in a transformer, it's actually way higher. Okay, so cool. So very simple. The process itself is kind of the same. Not kind of, it's the same. So in the test, they'll give you your output, a open circuit, voltage, current, power. So the first thing you need to calculate is my process to doing it. You calculate your angle, which is your theta. So the equation you're using for this whole thing is P. Blue kind of hard to see. I'll use red. So P is equal to V I cos theta. That is the equation you're using. Because you'll have the P, which is your P no load. You have your V no load, the I, and what this is, cos theta no load. So you calculate your theta no load, plug in the values for P, V, and I, straight from the question. And you calculate the angle. From the angle now you kind of set, because you can kind of use the angle to get the IW and the IM. So this is just the general equation for it. You really have to memorize this. But what you do have to know is basically these. So this I no load, they gave it to any question because this is your no load current, but there's a magnitude. So any magnitude itself, you have to convert it into the two form, which is your IW and your IM. So it's very simple. So if you want to calculate IW, will be your I no load cos theta, which you already calculate the value for the angle. And then this one for the IM, it would just be sine of the angle. Yeah, so that's what basically just have a J terminal because it's sine, right? And that's really it. So you'll get your currents from there, and once you have your currents, you can calculate your RO and your XM or your GXM if you want to be specific with it, right? So, well, the voltage is the same across both of them, so it'll be your voltage divided by your IW, which is basically this value here, and you get your RO. And the same thing for your XM will be a V divided by IM, which you calculated from before, and you get your value for your resistance or your impedance. That's literally all it is. So the process, calculate your angle. Once you calculate the angle, you could calculate your IW and your IM because IW is I no load cos of the angle and IM is the I no load sine of the angle. And that is it. Just remember the current for IM is a reactive current, so don't forget to pay J. For the real part, you don't need a J because it's real current, okay? And that is it. Angle IWIM ROXM. Same process over and over. It doesn't really change. Alright? So you all good with that? Cool. So as you
So like
yeah.
we had separate there, right? I, W, and IM, right?
Mm-hmm.
We like for exam conditions, like we had to convert it, like combine it together, like for the I no load. So it will be like
Yeah,
the
go ahead.
imaginary part. So
So
it
you're
will be
talking
like,
about the general equation, which is I no load is the I W minus the J I
oh
M.
my god,
Yeah.
yeah, yeah,
Yeah,
yeah,
yeah, yeah, yeah.
yeah.
Yeah. I mean that is the equation for it, right? But
Yeah.
if the only time you'll have to do that is if you need to calculate your I1 given a I in. Remember, I1 is your input minus the I no load. So you will only
Right.
have to do that if you have to calculate I1. Okay? But
Oh,
yes, you
okay.
don't
Then
have
to
to
do
do
that,
that.
we just combine these two here into
Yeah,
that form.
correct.
Okay,
Yeah.
cool.
Just I'm gonna stop playing positive because I think in your notes you have a negative here, right? We just use a
Yeah.
different equation. So don't worry, it's the same thing, right? So yeah. Good question. If you give an input current, you have to subtract your I load. The mistake there Yeah, input current is not necessarily your I1. Don't make that mistake. Okay?
Okay, and a follow-up question, right?
Cool, go ahead.
So if your IM, right, that
Mm,
current,
right.
would that ever be negative for it to like multiply out and give you a positive
Nah,
there?
that will never be negative. Ever.
Okay,
That will,
okay,
anytime you get a positive or something canceling like that, you do something.
okay, cool.
Because cos is an even function, the negative will disappear when you're doing it. But most
Oh,
of the time, that will never, based on the process. Because for open circuit, once you do the cos inverse of P, V and I, even if the P, V or I had a negative for some reason, which is wrong already, you're still not gonna end up with a negative angle. Yeah? And the units way for you to end up with a negative angle, I have no idea. Because the units way we get a negative is if you sine, because sine of minus theta is minus sine theta. That's the units way we get a negative out, right? But don't worry yourself, that is too trivial.
okay,
That's
cool.
too trivial, right? But yeah, that's just run through the stuff. Theta, IWIM, RX, same steps, never change it. Okay, same thing for the short circuit, but a little different. The reason why it's a little different because the short circuit compared to the open circuit. In the open circuit, your RO and the XM in parallel, and the short circuit in series. So you kind of get through. So the first thing when it's in series, so you basically just have this going on here. So you have here iron. Remember for the short circuit, only under short circuit conditions, your input is the same as your I1 because under high currents, your I no load is assumed to be negligible. Okay, so you have this, so you have your REQ and a J execute. So it's in series. The open circuit in parallel, so the calculation will change up a little bit. So real simple. The first thing you calculate is, well, you have this equation here. So from this equation, you can calculate your R, because P is equal to I squared R. That's normal power equation, right? So you can calculate your REQ from here. So in this case, it will be 6528.3 squared, which was your current, and you get your REQ. And from that REQ, you can actually use that to calculate your execute. All you need to do is just two more steps. So you calculate your Z, because V is equal to IZ EQ. The Z is the total. Remember, Z is equal to R plus JX. Always remember that, right? So you just calculate the REQ from before. ZEQ is the total impedance, which would just be the voltage divided by the current. And once you get this, all you need to do is a little bit of Pythagoras theorem. This is a triangle. So ZEQ is the hypotenuse. So you have your REQ and you have your XEQ. And if you do Pythagoras theorem, make XEQ the subject of the formula, you'll basically end up with this equation here. Now, you just plug in
So,
value.
so this
Go ahead.
triangle is a standard triangle, right?
Yeah, yeah, yeah.
Or label.
Yeah, it's
Okay,
on the
cool.
triangle. Because the X is G, which is our impedance, which is the
Oh,
vertical
Y
part.
and okay, real is X. Okay, that
Yeah,
makes sense.
same concept. So with that now, you calculate XEQ. One at the first thing you calculate Z, which is just the V1 and I1. And from these two, you can literally just use Pythagoras theorem and calculate XEQ. Yeah, that's literally all. That's the same process. The same process. So you have to get mind boggled if they give it to you. It's the same process going through. They have to give you the same values because it's a test, which means that when they conduct the test, they acquire the same values P, I, and P. Same thing like the lab. Okay, you just need to know the process to go through it. So for the short circuit, you just calculate REQ using the equation P is I squared R. You calculate Z, which is V1 and I1, and then we just use Pythagoras theorem to get the execute. All right, any more
So I
questions?
had
Go ahead.
one question.
Yeah, go ahead.
I can't remember if it like I remember for one of our labs. I think it was my first lab. We had to do calculations like these,
Mm-hmm.
and it had a different method. I think it was the complex method.
Yeah,
And it have a
I like that
complex
method.
method to do it.
I don't
Um,
use that method. I never
I
use
want
that.
to ask.
Yeah, go ahead.
for the exam, right?
Mm.
Would still specify which method to use
No,
or both
you can use any
methods?
method. Once you get the correct answer. For me,
Okay.
this method closer to
This
something I
way
would
is
remember because it's
yeah.
like REQ, Z, Pythagoras theorem. I can memorize that. But you see, when you start going to complex and it's like, that's too much.
Yeah, because like I realize when you do it in a calculator, you get like errors in
Mm-hmm.
like when you throw the whole thing in a calculator with the complex mode, like it is always get errors.
Yep.
And yeah,
Yeah.
so
So don't mix up the tests with the actual calculations with it. Because if you're doing it under load conditions, the you can't do these things. Because it's under loaded conditions, right? So the
right.
values and stuff will change up. But under test condition, you could do this. Just make sure you know if they say under test or under load. Okay? And that's that. Any more
Okay.
questions? Alright. Speak now or forever hold your peace until the finals. Okay, so I mean that's going to the proof. So I mean he doesn't really bring proofs. So you go through the proof. Okay, so I could go through this, but I don't want to, because I already went through this when I did the example with the transferring the impedances. All you have to know for this is that when you transfer the impedance, you just basically using the turns ratio and carrying it to the next side. And when you carry it to the next side, you add it up. Okay, you get two R's and you got two X's. Add it up, you get REQ and XEQ, which is basically Z EQ. Because Z is REQ plus J XEQ. That literally doesn't change. Okay, so in this question, I kind of help you to practice. So try it out. I have the solution here. So go through it, make sure you understand the transfer and however the cases, and you'll be good. Okay, all this was the same thing. Alright, so we can get into some questions. So I'm gonna run through this. Anything I say to write it down, remember it, please. Because I'm going through it in a way that I'm giving you the tricks that you try to give it in the question itself. Okay? So let's pay attention to the tricks. You have the solution here that go through it. But pay attention to the tricks. Because every question you do for power, he deliberately puts a trick in it to catch people. The reason why is Bago been lazy. He want people to make mistakes so he have less things to correct. That's how we just do our exams. But the mistakes aren't mistakes we trying to shaft you. It's just basic mistake people that overlook. Okay, so that's how it is. So any question, that's really question. The biggest tip I will give you all for power is always draw the equivalent circuit with the given values, which is why it's important to memorize your equivalent circuit and all of the parameters. Memorize all of it. When they give you the question, have it in your mind. You just plug in the values into that default or that draft. From that draft now, you should be able to go from anywhere, because one, you memorize the equations, and two, you already know how the ins and outs of the equivalent circuit does work. So you could never ever get catch. You could start from Jesus Big Two and you could still end up somewhere else because you know the ins and outs of it. That is the best advice. Try a circuit. Okay, you can see it in front of your face. Okay, so diagram, equivalent circuit, parameters. Okay, they give you n. Turns, okay, there's n1, n2. Cool. The no load current and core losses. Very simple, right? So there's the question somebody had asked where if you had to convert it back, yeah, so that's basically a good example of it. So your no load current, you basically know, okay, if it's a no load current, basically there's an open circuit test. So all the current are coming in, going straight into your no load. That's why they call it a no load, right? So same equation, that's what you told me before. And it's very simple, right? In the circuit, you basically just have a split coming back out, right? So if you have a voltage here, V1, these two things are in parallel, your arrow and your X. So since it's in parallel, the voltage up across it will be the same. Which means if you have the voltage, so there's V1 here and there's V1 here, because it's in parallel. Okay? V1, V1 here. If you wanted to calculate the current in each of them given the voltage and the actual value for it, you just kind of divide it because V is equal to IR. So I will be equal to V on R or V on X However the case is, I wonder if they gave you a circuit for this. I think I copy the circuit. Yeah, the kind of there they gave you a circuit. Yeah, so in this case here, right, forget about this. Yeah, there's a good example, the current, the input current. They gave you the current as a phasor. Well, not phasor, a complex one. So if I wanted to calculate the current here and here, the voltage at this branch here is 100, and here is 100 also, cut in parallel. So if I want this, it would be V divided by R, which is 0.5, and this one here will be 100 divided by the J50, which will get like minus 2J or something like that. So I can't remember who had asked the question, but in this way you can kind of piece apart the values. So we know 100 divided by 200 is 0.5, right? And we know this here will give us minus 2J. The reason being it will be 100 divided by J50. So when the J at the bottom, when you actually do the division, the J will go on top and it will become negative. Like why the negative does come from the actual equation itself. Okay? You end up with the Im minus J. Yeah, anyway, so if this is 0.5 and there's minus 2, you can kind of calculate what this is, because 0.5 from the real part is 1, and then minus 2 from here will basically just be minus 2. Because when you add these two back up together, you still end up with the input currents. Yeah, so this is actually a good example of the current splitting. Q. Any questions on that? Any questions? I assume not. So there you go. So yeah, so any questions? I already went through this. So IW, IM, you calculate your values and you put it back together. That is your no load current. Right? And then your core losses, which is your core real component, would basically just be the losses incurred across those 200 ohms. Do not, I repeat, do not go and do J50. That is reactive losses. You have no reactive losses because reactive power just circulates back and forth in the circuit. It is not dissipated in the circuit. Okay? So it's basically just you buying this stuff, the food supply, and you come back home like there. The only time the power or the food is lost is when I actually eat the food, which is the real losses. Okay, so yeah, core losses will be here, which is just P is equal to I squared R, which is 0.5 squared by 200. That is your core losses. This is not part of your losses. This is not part of your losses. This is not part of your losses. Do not use those things. Losses is real. So yeah, so you have your I squared, well like W in this case, arrow, and you get your losses. Real simple. Same process we used before. And then what's the next question? So the next question, the one, the secondary output voltage and the copper losses working on the primary side. So it's a fairly simple question, but what we have to do with the circuit, we have to do a little bit of manipulations on it. So you'll notice that the impedance is kind of all over the place, right? So because it's kind of all over the place, you have to get it on one side. Because if you don't get it on one side, you gotta do two voltage drop calculation, which is way too much. So all we gonna do, but any question kind of told you what side to work on. This how to work on the primary side. So if let's say you work on the primary side, you have to refer all the secondary stuff onto the primary side, add it up, and get one lump REQ and JXEQ. That's basically what they're trying to tell you, because it's on the primary side that you're working on, right? So in the question, you have to carry the 8 and the J24 across to the primary side. And I could eyeball this. When I carry the 8, it will be 8 multiplied by going to N1, you're coming from N2, all squared. That will give you your R2 prime, and your X2 prime will be your J24. You're going to N1 to the N1 on top, N2 at the bottom, but you're coming from N2, all squared. And when you add the equivalent on both sides, you will basically end up with the impedance working on the primary side. Okay, so that's basically what it is. So you have R2 prime, same thing, get your 0.5, and then X2, the same thing, it does easier as ratio, and you get your, this is J 1.5, and then you just add it up. So if you carry it on the primary side, it will be the 0.5 plus the 0.5, and it will be the 2.5 plus, I think it was the 1.5 when you referred it. These are the referred values. These values is what was there from before, And when you add it up, you get this. That's literally all it is. They will tell you what side to work on. Once you do that now, you come to this beautiful equation here, which is what I was talking about with the E1. So you have this, you can say this V1, right? It goes in, you have 100 volts here. You have the voltage drop across these components here, and I will give you E1. Remember in our circuit right now, this is a flat line, right? Because we refer all the impedances onto the primary side. So because we refer everything on the primary side, this is just one wire going straight to the output. So once I calculate my E1 and use my turn ratio to get E2, E2 will basically be output power, or output voltage, sorry. Yeah, that's basically why the say refer to the primary side. So that's what we did. So same calculations. The I1, we had calculated the I1 from before because in the circuits, I kind of walked through it already. When you calculate your no load, your I1 is basically your input current, which is your 1.5 minus your 4J minus your no load current because it's KCL, right? And that will give you your I1. And you can kind of eyeball it from before. So you have your 0.5. So 0.5 minus 2J. Obviously, what you had to add to this to get it was 1.514. So if you add 0.5, then you go back, it will be 1, and this will be minus 2. Right? That's all this is. So that will basically be a current I1 and the ZEQ. You already calculated that from before, which is referring everything on the primary side. Calculate in complex mode, plug in the value, you end up with the answer. So you end up with this. And
So I
then,
have a question.
go ahead, sure, no problem.
For the calculations, right?
Mm-hmm.
I think Justin was talking about that, but we calculating in the complex form.
Yeah, you have to pay a calculator in complex mode because you
No, I
have
mean
three
like the
steps.
complex form here with
Oh,
the J values
the 1
because
plus 4G thing.
yeah, because if you're calculating the phasor form is be different
Mm,
values you might end up getting.
no, I've never experienced that before. Well, it depends on the type of calculator you have. I have a Casio, so it don't matter what form I pay. That has never happened to me before. Most of the time, I will convert it, but either way, if I put complex and phasor, my calculator will be the same way. But have you tried doing it with both and again a different answer? That's the
Yes, so
question.
for the lab I tried doing
Mm,
it with the complex and the
mm,
phasor
mm.
and it was different values for the answers.
Okay,
It
well,
was like slightly off.
most of the time will be slightly up, but it have a tolerance in it. It have no fixed answer, but it have no right or wrong way to convert. Because you technically you will add in complex and multiply in phasor, but personally, from a electrical engineer point of view, it don't matter. It don't matter because the calculator cannot make that like large of a mistake when you do the calculation. It might have some discrepancies, but that discrepancy wouldn't give you the value wrong. The answer wouldn't be wrong. Yeah.
All
So
right.
he's not gonna
Cool.
take away mark because he didn't convert it or something. And the calculator should not give you the wrong answer unless you plug it in wrong. Anytime you're doing that, what you have to do, you have to use brackets to separate everything. Especially when you play in different forms, make sure and use your brackets for everything. Like literally bracket off, bracket off, bracket off. So they will know, okay, they're separate. Because the calculator could convert. Because I don't know if you all notice in your calculator, you could kind of click shift and mode or something, and it could actually convert it from phasor to complex. I don't know if you saw that before. So that means the
Yes, so
calculator
that
knows how to convert from complex to phasor and phasor to complex. So if you put in both, it will know to convert it to whatever form. So it knows how to do it. That everything don't have to be in one form. So just make sure when you're doing it in a calculator, make sure I'm bracket it off. Yeah. I did this tutorial and my calculator, everything was in a phasor form. I just have to convert it back. It don't really matter. Get the same value.
okay.
Right? But good question though, but it don't matter. Yeah. So once you get E1, so going back, right? So once you get E1, just use the turn ratio and you get the E2 and you get your value. Make sure and put back your angle though. And when you're doing a turn ratio, that's using the magnitude. I mean, if you put the angle in a calculator and you multiply by the turn ratio, you get the same answer. So, don't matter. But when you're doing a turn ratio, just use the magnitude and put back the angle. The angle not going to change. Okay? And what this was the answer. That is your E2 and your output voltage because you have no impedance on the secondary side because you refer to the primary side already. So you have to do it twice. Okay? And then your copper losses, which is the losses in the coils itself, is basically just your Req losses. So basically just be your I1 squared Req. Why? Because I1 is the current going through Req. So power is I squared R, plug in your values, and you basically get your answer. Very simple. So your total losses in your circuit now that we come across. So P losses is basically just be a P core plus a P CU. CU means copper losses. So I'm going to just put CL. These are the only two losses you have in the circuit. Copper losses and your core losses, which are real. So this is I O squared RO, which and then this is I1 squared REQ. Only two losses you have in the circuit, have no others. You have no reactive losses in the circuit. And what was the last one? Okay, so the load impedance. So the load impedance, a lot of people ask me about this. Not as difficult as you think, right? So if you want the load impedance, right? All you need to remember is that you have a voltage and you have a resistance. Either way, you'll get the same answer, right? So yeah, once you have a voltage and a current and you divide it, you'll get a resistance. That resistance or that impedance is the total impedance seen in the circuit itself. So all you need to do this to get your load, you just divide the input current, or sorry, the input voltage by the input current. And once you do those two, you just refer the value onto the secondary side, and that'll basically give you your secondary impedance. That's all it is. Because V is equal to IR. R is Z. So if you have V and you have I, if you divide those two, you basically get the impedance. That's really all that you're trying to do. Okay? So either way, you'll get the same answer. I'm looking to see where I did that. I think this is a difference. Either way, that's here. I'll check and see my notes. But yeah, that's all this is. V is equal to IR, your input voltage divided by your input current, or if you have the on the secondary side, that is probably the easier way to do it. So let me show you that way. So on the secondary coil, you have your resistance, you have the inductor like normal, and you have your load. So this voltage here, so you have a voltage V out, right? And then by default, you'll have your I2 current. So if I wanted to know what this impedance is, V is equal to IR. So therefore the R here will basically be the voltage divided by the current. So this current is I2 and this VL. Yeah, that's probably the easier to do. Obviously in the lab itself you'll have an angle for the power or for the voltage. So therefore you end up with the real and imaginary part. Yeah, so that's really all it is. V is equal to IZ. So Z is equal to V and I. So all you need is the voltage at the output and the current. If you have the primary values, just calculate I2 turn ratio. Most of the time if your impedance is on the primary side, the induced voltage will be a VL because you have no impedances on this side. So you get through. Alright, that's how you do the load impedance. Voltage and current to the load, give it the load. Normal calculations. Cool. Any questions on this? Cool. Alright, so everything else is mostly the same process. So in this question, they gave you the load impedance. Just keep that in mind. And they said the load is inductive, which means the angle negative, and they gave you the ratio of the secondary to the primary terms. So they want the input primary current. Note that the impedance is on the primary side, which is okay. I'm not going to change too much. So the first thing that you will want to do is calculate the or just refer these on this side. The reason why is because they already gave you this load here. And if you have the load and you refer these on this side, once you have these two, you have the total um impedance on one side. And basically working with is once you have the total impedance on one side, you can calculate the current because you have rated input. So you have a ratio. So watch it. If you refer these two onto this side, you have no um, impedance on this side. So it's just a straight wire. So if you have 200 volts here, this will be 200 volts. And they gave you the turns ratio. So basically this 200 on this side will get 2000 here. So once you have the 2000, you already lump all the impedances and carry it across on this side. So you have an impedance here, you have an impedance here. So basically V is equal to IR, and then from there you can just work backwards. So you have the V I2, and you have your R. Well, in this case, the R will be the total for here and here because it's like a circuit you have. So I2 will basically be the 2000 on your R. Come in, come in. So now, so once you have your I2, this is just the magnitude of the current. You're missing one thing, which is the actual angle for it, which is all we're trying to explain to you, right? If they give you this load, you can actually calculate the angle for that load. And if you calculate the angle for that load, that will be the angle of the current. And if they say is an inductive load, which means that the angle will be negative. So you will end up with the angle for the current from that. Yeah? Which is why I told you, once they give you the load, you have an angle. That angle is the angle for the current. And have to tell you if it's lag or lead, inductive or capacitive, to know the angle for the current. So you can get this, which is the magnitude, that is okay. You can get this, which is the angle from here. Normally they'll give it here as a power factor, or sometimes you could give it here as a complex form. If you have a complex form, you could just do your normal tricks to calculate your angle from that, and the angle obviously will be positive because you can have a negative load. But you just have to know that when you're actually doing the angle itself, if they say it's inductive, the current angle will be negative. Okay? So I just have to
So,
yeah, go ahead. Go ahead. Mhm.
a question.
Yeah,
I
go
don't know
ahead.
if I take it right, but so basically, an inductive load will
Mm-hmm.
give you a lag or a negative current, and a
Correct.
capacitive load will give you a positive or a lead.
Correct. Practically,
Okay, cool.
you have you don't have that much capacitive loads. Inductive load are things that have a coil in it, which is like 90% of things in your household. Kettle, stove, fridge, fan, your phone, charger, every charger in your house have a little transformer in it, which is aka a coil, which is aka inductive, right? You really have any capacitive loads in a circuit itself. So you don't worry about that.
Okay,
But yeah, inductive, the angle will be negative. Because the voltage had to happen before the current. The current can happen before the voltage. Like that that really makes sense in power. Yeah, you need the voltage before you had the current, right? Alright, any more questions? Alright, cool. But the concept is you refer the impedances on the secondary side. You have a load, you have this. When you add these two up, you get one impedance. You have the voltage because remember when it refer, you basically end up with a line. So you know this is 2000 because here have to be 200. It have no voltage drops because you carry the voltage up on the side. So you're accounting for it here, not here. Alright? And once you do that, you just end up with an impedance. You have the voltage, you can get the current, the magnitude of the current. And to get the angle, well, they give it in complex form, you get the angle. And then inductive, so it'll be negative. And you just pair everything together. So that's a good question in terms of bringing everything together. Yeah, just remember the small stuff. So if they give it to you, you see it in the question, you will know what you could get from it. So you won't be too confused from it, right? Anyway, so I go to the solution. Well, the solution is, so let's go through. Yeah, more questions?
Yes, sir.
Yeah,
Well, I was now watching the solution there. I realized implies that the primary current, you just take I2 and use the turns ratio to find it.
Yeah, correct.
Yeah,
Mhm.
yeah. Okay.
That's the concept because I don't have enough information to get I mean, I could, but I real circuit theory. Because if I had to do that, I got a strain here, right? You all don't need to do this. You could have used circuit theory, but I don't think you all do circuit theory. I don't know if you all do circuit theory. That probably a semester 2 year 3. You'll have to do this in parallel with this and this already in parallel. So you do parallel here, convert it to one impedance, and that they will be in parallel with this. And when you do that parallel now, you gotta divide the 200 by that resistance, and then you can get the input current. But that's plenty work. Alright? So the easiest way to do it is first carry that stuff on that side, find I2. And once you find I2, you can use the turn ratio and find I1. And then clearly from here, you all could see that you could calculate your I no load. Really easy because we literally did it in the previous question. 200 divided by 400, and then this divided by that, you'll get your I no load. And remember, your I in is basically your I no load plus your I1. If you had just say I1 and that was the answer, you'll get it wrong because, as I said, the input current is your no load current plus your I1 current. Okay? So just be careful how you're doing this stuff. Right. But the trick is to know what you have to do. If they give you any information with the load, most of the time you have to start from that side, which means refer everything onto that side. If they give you more information with respect to the input part, refer everything to the primary side. You're just working on the side that you have the most information for. Yeah, you don't have to work on the side that they give it to you. You just work on the side that you have the majority information for. On the secondary side, they give you the impedance, they give you the angle, they give you the angle for the current, and you can get the magnitude of the current if you just refer everything onto that side. Well, so yeah, so just keep in mind just work on the side of the most information. Okay, so yeah, so same thing. You refer, that's like how I explain it. When you refer, you get this nice circuit. I just explain how you get the 2000 because 200 flat turn ratio 10. 200 by 10, 2000 because you have no losses on the primary side. A nice circuit series, everything in series. So you add everything up, I2, you divided 10, you get a value. So this angle here, if it does work with everything, you will just end up with the angle from there. You don't have to worry about it because you already have everything in terms of G's. So you end up with the I2. Flat, complex form, you get your angle. There's the angle for your current. Yeah? So then now, well, I mean, you just use your turn ratio as the guy was saying. You multiply it by 10, you carry it back on the I1 side. This is just I1. So now we have to calculate your no load to then add it to the I1. So that's like before. Your I no load 200 divided by 400 minus your 200 divided by 231. And you get your no load current. And you just add it up. And you get input current. That's literally the process. So the process was I2, turn ratio, I1, I no load, in, I no load plus I1. Same process. Any questions on that? Alright, cool. Alright, what was the next question on this? Right, the secondary terminal voltage. So terminal voltage basically just another way to say was the output voltage. So if you see terminal voltage, you get confused. Just means the terminal voltage is the voltage you're actually measuring at the terminals, which is basically the voltage you're getting out after the losses. And luckily for us, we already have all the impedances on the secondary side. And we have I2. So I mean, I don't know what else we want. So if I want the voltage here, you have the 2000, you have your REQ and your XEQ, normal circuit theory, 2000 minus the voltage drop across your REQ plus your JXEQ, and that basically give you a V out. Normal circuit theory, okay, you have 2000 here minus your losses, you get V out. That's all. That's all. Nothing to bust your brain. So this was the question. So yeah, that's exactly what I did. Because you already have everything on one side. You have I2 already. You have your losses. And you have the E2. E2 is the coil voltage, right? And that's really all it is. Output voltage. And efficiency. So the efficiency part is where you have to keep in mind that you need the power factor for the load. Right? So the reason why we're using this one with the V2 is because I already have I2. I literally just calculate what V2 is, and well IW and I2, well we have I2 already. So we literally have majority of the information on the secondary side already. So I'll just use the equation that have everything in terms of 2, which is the secondary part. And that equation will be the output divided by the input. And in this case, I will add the losses. Just know the two equations. Okay? So to do this, since you're working on the load side, you need to actually calculate the power factor for the load. And you can do that because they already give you the actual load in complex form. So from this, you can calculate the angle from it. And since it's a inductive, I mean, that is really all you need. Because cos inverse that will be, well, just cos of the angle will basically be a power factor. You gotta inverse that one. And that is it. You don't need to really care about the negative. If you did, you still get the same answer because cos is an even function. Yeah, so that is what I said. Once I gave you the load, you have to calculate cos theta of the load. Alright? So with that, they give it in complex form, you get the angle. And cos of the angle is your power factor. I need to use the power factor. What does cos theta, which is your power factor, in the efficiency equation, which is this here. Which is why I said you had to calculate it. Now you have V2, you have I2. You have these already. So I mean just plug and play at this point. So for the currents, for efficiency, you don't need to put any angle. So if your current at an angle, so you're just using the magnitude of it, not putting the angle in the calculator, okay? Just the magnitude alone. Right, so we have that, we have this power factor, V2, I2, your cos theta, same thing. So normal equation, and you have your losses already. So this is your IO squared RO, and this is your I2 squared REQ. And that's the answer. That's all. Very simple, straightforward. Right, any questions on that? But the trick in this one was he gave you a load, which means he gave you the power factor of the load indirectly. Yeah, that was the trick in this one. Alright, any questions on this one? Cool, guess no questions. Alright, so I mean, this is similar to what we did before. Okay, so they gave you the question. They said the equivalent series impedance refer to the high voltage side. The high voltage side in this question is your primary side, because based on they give it here. They give you no load losses, okay, and the output voltage on the secondary side. When the transformer is delivering a rated load, well, basic example of them giving you a load, and the input voltage is maintained at this. Okay, so they want to know what the output voltage on the secondary side is, basically, and they gave you what the input, which is V1, is. They already gave you everything referred to the primary side, so basically the same format where you have to go from the input voltage, get I1, get the losses, E1, turns ratio, and whatever E2 is will be your V2, based on how they gave it here, because they said the equivalent impedance already referred to the high voltage side, which is the primary side already, so you don't have to worry about doing too much. So basically you have this here. So you have this coming in, everything referred to this side already. You just need to calculate E1, and well E2 you just use your turns ratio, and you basically get on that side. The trick is